तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the section 1 we had discussed diode, basically a 2-terminal element. In this section, section 2, we will be discussing amplifiers, one of the important signal processing element block. As against the diode, which is a 2-terminal element, this can be now this has to be a 3-terminal element. There should be an input port or input pair of terminals, and there should be an output pair. This is called input port, this is called output port. This is the black box. Okay. So, input port is nothing but a pair of terminals here, wherein input variables appear, which could be input voltage and input current, input voltage and input current. Output port is the other pair where the output voltage and output current appear. Normally, we are going to have something called load here, that is a load resistance, onto which the output is going to be fed. It could be another stage also, right, of amplification. So, that means it will be later on maybe cascaded to another stage, whatever be, that will be the load for the amplifier stage. This is going to be fed by what is called a source. That source can be represented as a voltage source with a series resistance Rs. This is one way to represent the source. These are either as a voltage source in series with a resistance, or this could be also represented as a current source in shunt with the resistance. And using Thevenin's theorem, you have seen that any non-ideal source can be represented either as a voltage source in series with the resistance or as a current source in shunt with the resistance, in which case we can say that this is equivalent to as long as I s is equal to what is called as the short circuit current in this particular case. This is shorted, the short circuit current is V s by R s. So, that is the value of I s. So, these are exactly equivalent. This is Thevenin's equivalent for a source, this is what is called Norton's equivalent for a source. So, any source which is exciting our amplifier, this source is therefore sources. These are necessary to excite the amplifier, right. Any source that is necessary to excite the amplifier is going to be non-ideal, assuming that it is non-ideal, can be represented as a Thevenin's equivalent, so voltage source in series with the resistance, or as a current source where the current value is nothing but the short circuit current Vs by Rs in parallel with the resistance. This is the equivalent. These theorems you have already studied in your networks course. In the same networks program, we have also learned something about what is called two-port networks. So, the part that we have learnt in the two-port network, we have to revise now in order to understand and appreciate what is happening with amplifiers that we are going to design and use. So, let us therefore try to understand about first ideal amplifier. Just as we understood ideal diode and its application, and later on saw how non-ideality brings about some modifications in what is called the equivalent, okay, and then how this can be incorporated in the analysis. Same way, we will now use this two-port theory in order to understand about amplifiers. See what are ideal amplifiers, what are the types of amplifiers available, and how these can be realized in practice later. So, this exciting source could be another amplifier feeding onto this. So, in a general situation, this could be one amplifier feeding onto this primary amplifier of ours, which can always be represented as a voltage source in series with a resistance, and it could be feeding on to another amplifier, okay, which could be treated as the load, or you can have an independent source here. Okay. So, let us talk of independent sources. What are independent sources? Independent sources are our signal generators, maybe the sine wave signal generator or audio signal generator, okay, it is called, or it could be the transducer, which is converting, let us say, mechanical energy into electrical energy, okay, that also can be represented as a source, or whatever we had discussed earlier, an LED, okay, which is converting light signal into electrical signal. Okay. So, that is the LED output can be used here, or we can use also let us say solar cells. Okay. The light from the LED can be used to fall on a photo detector, okay, and that can be used for further amplification, etc. So, we can convert one form of energy into another energy. We can use the LED as the load here and convert the analog signal, electrical signal, into light signal, and again process it further if you want. This light signal can be converted into a source here by using let us say photo diode. Okay. So, these days with the availability of optronics, this kind of conversion commonly takes place, converting electrical signal into light signal and back into electrical signal. So, basically independent sources are all those which can generate electrical signal from some other form, mechanical or otherwise. This could be let us say a microphone which will convert the sound signal into electrical signal, or this could be a speaker which will convert the electrical signal into sound signal. So, we have independent sources and the amplifiers are now called dependent sources. So, this is the distinction between independent source, which could be a transducer, okay, or let us say which is photodiode, okay, and let us say pressure transducer, strain gauge, okay, microphone, this could be a transducer, independent sources, or just plain electrical signal generators, test signal. This is to test these amplifiers, etc. We could plainly apply, okay, test signals at the input. So, amplifiers are dependent sources. This is what we have to understand. That is, the parameters here V naught or I naught could be dependent upon V I or I I. The output parameter V naught or I naught, okay, could be dependent upon V I or I I. Consider an ideal situation here, that this is an open circuit. This is an ideal situation now I am talking of. This is an open circuit, in which case I is automatically 0. So, if the input port okay, open circuit, then obviously I is 0, which means this amplifier becomes voltage controlled. We will abbreviate it as VC, voltage controlled. So, if the input port is an open circuit, then I is 0. It is controlled by only Vi, and because I is 0, Vi is same as Vs. Okay. Nothing is lost in the source resistance. Whatever be the source voltage is going to appear as input voltage to this amplifier. So, then we call it as voltage controlled amplifier. Okay. The output can now have its current dependent upon voltage or its output voltage dependent upon input voltage. Let us consider again an ideal situation here, one of those, where output voltage is dependent upon input voltage. So, we will now say that output port is going to be a voltage source, ideal. So, output port is going to be an ideal voltage source, whose output voltage is going to be dependent upon the input voltage. So, we will call this as, let us say, K times V I. So, if it is therefore the output port, we can now draw a voltage source, ideal voltage source, that means its source impedance is 0, right. So, V naught is going to be K times V I, because its source impedance is 0, right. This V naught is going to be same as this source voltage. So, V naught is equal to K times V I. Now, this is therefore called a voltage source. So, what is it? This kind of amplifier is therefore called voltage controlled voltage source. This is one type of amplifier. Voltage controlled voltage source. If therefore I have this as non-ideal, obviously, right, then I might have a what is called as an output resistance, which is non-zero for this. This becomes non-ideal. At the output it becomes non-ideal. Then I might have non-infinite input impedance, so in an ideal voltage controlled voltage source, Ri is infinity, R naught is 0. Is that clear? This is called an ideal voltage controlled voltage source. This is one of the most important amplifiers that is possible ideally, okay, where input port becomes voltage controlled. Now, this is something that we have to understand. It becomes voltage controlled when II is 0, going towards 0, that the input current is extremely small. The value of Ri should be very large. Now, large compared with what? Now, any comparison here in practice should be made with reference to what it is going to get as input. This input voltage here is going to remain undisturbed as Vs as long as II is 0. That is possible when only Ri is very high, compared with what? Compared with Rs. Okay. So, this is a voltage source drive as long as Rs is much less than Ri. That means, in a practical situation, I can call this system, which is being fed by a non-ideal source, into a non-ideal port as voltage controlled as long as Rs is much less than Ri. In such a situation, right, Vi is going to be very close to Vs. So, this port becomes voltage controlled. So, practical VCVS therefore has Rs much less than Ri, and similarly here let us understand it on the output port. KVI should be very close to V naught. That can happen only when the drop across this is negligibly small, which means RL has to be much greater than R naught, or RL has to be much greater than R. So, in a practical amplifier, you will call this an amplifier which is close to voltage controlled voltage source if you know what is the source that is feeding this amplifier and what is the load. So, given the source and the load, I can call this a voltage controlled voltage source amplifier only when I have RS, the source resistance, okay, much less than what is called as input resistance of the amplifier. So, Ri is called input resistance. By the same thing, I can call this really voltage source as the output dependent that is dependent voltage source only if RL is much greater than R naught, which means R naught is called the output resistance. These are the important parameters of the amplifier. Input resistance. Okay. What is input resistance? It is nothing but VI divided by II. Suppose therefore, I look at it here, voltage across this is VI, that divided by II is defined as input resistance. Okay. So, this is VI by II. And at the output resistance is going to be very small compared to RL, then we call it a voltage source output. Okay. And how do we measure the output resistance? It is very simple. If VI is 0 and I excite this by V naught, then V naught by I naught is going to give me the output resistance. Remember, this dependent voltage has to be made 0. How do you make? Put Vi is 0. So, this voltage source is going to give 0 output, and then excite here by means of a voltage, we call it V naught, excite it by V naught, then the current drawn I naught is going to give me R naught. So, V naught by I naught when Vi is 0 is defined as the output resistance for this. So, output resistance and input resistance are important parameters of this amplifier, which we are calling as voltage controlled voltage source amplifier, in case these relationships are satisfied. So, the ideal voltage controlled voltage source on the other hand has Ri equal to infinity and R naught equal to 0. Yeah. The most important parameter of this voltage controlled voltage source amplifier is K. What is K? K is defined as open circuit voltage gain. What is it? When the load is infinity, because if it is non-ideal, the load has to be infinity. If the load is infinity, open circuit output, it is open circuit, output is open circuited, then output voltage is same as K times Vi. So, this K is called open circuit voltage gain. That is, what it means is open circuit means RL, okay, is equal to infinity, or in the case of ideal voltage controlled voltage source, R naught is 0. Okay. So, V naught is going to be equal to k times V I, there is no problem. The only parameter that will exist then of significance in the case of an ideal voltage controlled voltage source is k, the voltage gain. Therefore, this is what is called voltage gain. Now, let us see, let us do the analysis here. V I is going to be equal to R I by R I plus R S in practice times V S. Look at this resistance, this is another resistance. So, it is going to get attenuated here. This signal V S, because of its finite source resistance, is going to get attenuated and it is going to appear as R I by R I plus R S into V S, which means if it is voltage controlled, this factor of attenuation is going to be very nearly equal to 1, and this is not going to get attenuated at all, because R I is going to be very large compared to R S. Then we call it as voltage controlled. Okay. Otherwise, it is going to get attenuated a lot. That is not the purpose of a good amplifier. Okay. The moment you connect it to the source, drastic reduction in input voltage occurs. So, a voltage controlled amplifier therefore, will be highly suitable for this kind of source with source resistance which is very small. Now, look at the output circuit, k times V I is going to get divided between R L and R naught. So, the actual voltage we will call as V naught is going to be equal to k times V I, that is the source, divided by R naught plus R L into R L. So, if you mark this as plus minus and this as plus minus, then V naught is going to be k times V I into R L by R naught plus R L. Or now, if you want to find out what is the output voltage in terms of the source voltage, then we have here k times R L by R naught plus R L times V I, and V I will substitute from this, which is R I by R I plus R S times V S. So, you can see that the actual gain of the amplifier is going to be k, which is the open circuit voltage gain, times the attenuation suffered at the output, which is R L by R naught plus R L. Had it been ideal voltage source at the output, then R naught would have been very small compared to R L, and this factor also would have been very close to 1, and this factor would have been close to 1, and output voltage is very nearly equal to open circuit voltage gain into the source voltage. So, if you have a good amplifier which is voltage controlled voltage source, then this is going to be very close to k, which is the open circuit voltage gain. Okay. Now, there are certain terminologies here. This circuit is said to be unilateral. What does it mean? It's something that you have seen bilateral earlier. That is, whether I apply voltage here and obtain a voltage there, or apply voltage here and obtain a voltage there, okay. There is transmission in both directions, okay, and it almost behaves in identical fashion in both directions, let us say. Whereas, in this particular case, When I apply Vi here, this Vi gets transferred to this side as k times Vi, and the effect of that appears here. So, the transmission is possible only in one direction. In the other direction, when I apply a voltage V naught here, if I apply an independent source here, nothing happens to it at the input side. That means, input is not influenced by what happens at the output, whereas output is influenced by what is happening at the input. That is called unilateral. That is, only in one direction signal is transmitted. In the other direction, no signal is transmitted. An ideal amplifier, therefore, is unilateral. The ideal voltage control voltage source is unilateral, and the practical voltage control voltage source that we have now shown is still unilateral. There is no effect of what happens at the output at the input side. So, most of the amplifiers that we are going to discuss can be considered unilateral approximately, right. There is very little of transmission that is going to occur. That also, if it occurs, it is going to be occurring to a very small extent, which can be neglected. Now, if there is some effect here from this side to this side, obviously this V naught or I naught has to be represented as a source here, and that is called feedback. What is at the output is fed back to the input port. So, if there is some effect due to V naught or I naught at the input port, that has to be represented as a voltage or current source, right. And that is called feedback. And in a unilateral circuit, there is no feedback. In a unilateral circuit, there is only feed forward. The signal feed is only in the forward direction. There is no feedback, or the feedback factor is 0. So, the feedback factor is 0. That is what, there is no interaction of what is happening at the output at the input port, whereas what is happening at the input port is getting transmitted to the output. Now, this has to be very, very clear. Now, obviously, we can represent this in the two-port parameter method. Let us see what is this two-port parameter. Before we go to the two-port parameter, I would like to also discuss what exactly amplification means practically. Amplification, this is something that I've always means, right, power amplification. Amplification does not really mean only voltage amplification or current amplification. Amplification always means power amplification. What is power? Power at the input, there are two ports here now, therefore, we have power fed at the input and power fed at the output. So, input power is I into Vi. Output power is I naught into V naught. And therefore, power gain is nothing but output power divided by input power, which is, what is it? V naught I naught divided by V I, which is a very significant relationship. It is this that we want in every amplifier. If we get V naught over V I as a factor greater than 1, then even if I naught over I I is less than 1, there is still power gain possible. If V naught over V I is less than 1, as long as I naught over I I is greater than 1, there is still power gain possible. That is why voltage amplifiers as well as current amplifiers, okay, still are suitable for power amplification. So, this is something that you have to, in a passive device, 2-port network, let us say. If you take a passive network comprising of only resistors, capacitors and inductors, then you can prove that V naught I naught divided by V I I is always less than or equal to 1. For example, if the network that is put in the black box is made up of only ideal inductors and capacitors, then you can see to it that V naught I naught divided by V I is always equal to 1, because there is no dissipative element in the whole structure. Okay. What is inputted will appear as output. This is a classic case of a transformer, for example. Right. You put a transformer, for example, you can get V naught greater than V I, but I naught by I will be less than, okay, 1 by the same factor by which it is greater also. So, that the multiplication becomes equal to 1. So, in the case of a transformer, ideal transformer, V naught I naught by V I is equal to 1, whether it is stepping up voltage or stepping up current. It is of no consequence, it is not an amplifier. An amplifier is one where V naught I naught by V I is greater than 1, and therefore, the fact that it is magnifying voltage does not necessarily mean it is amplifying. The fact that it is magnifying current does not necessarily mean it is acting as an amplifier. We should always find out what the power amplification is, then only we have this unit becoming an amplifier. Such a thing is possible using what are called as active devices. These active devices could be anything that we can think of, the technology can think of. This could be tubes, this could be transistors, bipolar or field effect transistors, this could be op amps. So, these active devices are the ones which, if designed properly, which if biased properly, can give you power amplification, not always guaranteed to give, but if you coax them to work for you by designing them properly, by biasing them properly, they might give you power gain. They might work in a range where amplification exists. So, this is an important thing, and therefore, we will also know what this unit is. This is a ratio. This is normally expressed in terms of decibel. What is it? This is nothing but 10, deci indicating 10, log to the base 10 of this ratio. So many decibels, because in practice, if for example, input port is an open circuit or very nearly an open circuit, we know that II is 0. That means input power is going to be 0. So, this is going to be 0, but there will always be output power. So, most of the amplifiers that we are going to discuss will have either II very close to 0 or VI very close to 0. We will consider those amplifiers also. So, we will have these factors going towards 0 most of the time, and this is finite. So, this factor is very, very high, close to infinity, which means it is better to express this as a ratio, okay, rather than ratio converted to decibels rather than leave it as a ratio, which is going to be a huge quantity. Right. Now, let us try to work out an example. An amplifier, we do not know what type of amplifier it is, we will come to know only after we go through the entire problem, with Ri equal to 100 kilo ohm, Ri equal to 100 kilo ohm and R naught equal to 1 kilo ohm, is excited by a voltage source with source resistance equal to 10 k. So, automatically source resistance is 10 k and Ri is 100 k. So, it is a voltage controlled block. So, Rs equal to 10 k and RL equal to 10 k. Obviously, at the output resistance is 1 k and load resistance is 10 k, it is voltage source. So, obviously, the amplifier now can be categorized as belonging to voltage controlled voltage source category. The open circuit voltage gain is 10 to power 3. So, the k value is given as 10 to power 3. Determine the voltage amplification factor V naught over Vs. So, now this is a very simple problem which is normally encountered in any amplifier. Okay. So, V naught over Vs, from this diagram you can now see the diagram, is going to be 100 divided by 100 plus 10 times Vs into 10 to power 3, okay, multiplied by 10 divided by 10 plus 1. Okay. So, 100 divided by 100 plus 10 times Vs, okay, is going to be Vi, and that is going to be multiplied by 10 to power 3 appears at the output, and that is going to be further attenuated as 10 divided by 10 plus 1. So, the answer is very simple. So, we have it here as 10 by 11 to 10 by 11. Okay. So, 10 by 11 squared times 10 to power 3. Which could be converted into sort of decibels. This is something that you have to be very careful about. We have defined 10 log to the base 10 of power ratio as, okay, decibels, whereas if it is voltage ratio, okay, V naught squared divided by Vi squared, okay, V naught squared divided by, let us say, RL, okay, Vi squared by Ri, RL and Ri being equal to the same value, that is the definition of voltage ratio, okay, in which case this becomes equal to 20 log to the base 10 of voltage ratio, or it can be put in the current ratio also, right. That is voltage taken across the same load, okay, both in the case of output as well as input. That power okay, expressed in terms of voltage ratio or current ratio will turn out to be 20 log to the base 10 of V naught over V I. Okay. If you are expressing therefore this in terms of voltage ratios, you should put it as 20 log to the base 10 V naught over V I. If it is power, okay, 10 log to the. Similarly, current ratio also is expressed always in terms of 20 log I naught over I. Okay. So, if you are going to express voltage ratio in terms of decibels, then this will be very nearly equal to 60 decibels, right. This is going to be 20 log of this factor, which is going to be very nearly equal to 60 decibels. You can calculate it exactly as a homework problem. Please do calculate it. It is going to be very nearly 60 decibels. Okay. Now, I would like to at this juncture introduce you to other types of amplifiers. This is not the only type of amplifier existing. Obviously, we just said it could be voltage controlled voltage source. Instead, it could be current controlled. What is the difference between voltage control and current control? This is something that we have to understand now, because only in the present day electronics people are coming up with other types of sources which are more important than the so called voltage controlled voltage source, which was traditionally in existence as an amplifier. Okay. So, we should learn about other amplifiers equally well. So, current control, what does it mean? We just said in the case of a voltage controlled situation, I was 0 or Ri was infinity. In the case of current control, obviously, and it is controlled by Vi. In the case of current control situation, we will have Ri equal to 0. It is a short circuit. Here it was an open circuit. Here it is a short circuit. Ri is 0. Okay. That means Vi is 0, and it is controlled by II. Is the distinction understood? In the case of a voltage control block, II was 0, for which to happen Ra had to be infinity. We called it open circuit at the input port, open circuit port, and it was getting controlled by Vi. Now, this is a short circuit port. Ri is equal to 0. Consequently, Vi is equal to 0, and it is controlled by II. And therefore, we had to learn about this amplifier, which is current control, and it could be, instead of a voltage source, it could be a current source. So, output port, this is the case of input port situation. Output port could be therefore an ideal current source. So, we get this block as current controlled current source as a second important block acting as an ideal amplifier. First type was ideal voltage controlled voltage source. So, this is ideal current controlled current source, second type of amplifier. So, how do we represent this? So, this will be a short at the input port, and a current source. So, if I is the input current, V I is 0, and output is going to be k times I. Okay. And this is the output port. This is connected to load. Obviously, we must drive this, okay, again by a non-ideal source, whatever it is. So, we would rather drive it using current source, okay, which could be ideal, or when it is non-ideal it can have, because we will not use the other source, it cannot become ideal, right, because it is a voltage source, it will get shorted. Right. So, we will do it a current source which could become ideal with this going to infinity. So, R s. So, this is the way we are exciting. This is the same non-ideal source I s shunted by an R s. Okay. So, this is called, compare this with the other amplifier, this is now called short circuit current gain, because in case this also has non-ideality, which is the output impedance here, right. So, if this has non-ideality, which is the output impedance, then this current is going to be the short circuit current. Okay. So, this is called short circuit current gain. So, K is called short circuit current gain. This is a current amplifier as against what we had discussed earlier, which is a voltage amplifier. This is called voltage amplifier. This can now be called current amplifier. Ideal voltage amplifier, ideal current amplifier. In fact, ideal current amplifier, close to ideal current amplifier, we have got devices. Let us see how the practical devices are close to this.